Hello everyone, welcome to another class. At this time, we'll be looking at the conduction of electricity in gases, and I will hope that you pay rapt attention in this class as I share my screen and we dive in straight up. So like I said, we're looking at the conduction of electricity in gases. Conduction of electricity in gases. Now, the idea is I'm going to start with the condition for discharge. For discharge to occur, there is a particular condition that we must have. And what do we mean by discharge? For discharge of electrons. So, experiment, let me state it like this. With discharge tubes, show that gases conduct electricity under low pressure and hold on for a bit, let me change the color. Under low pressure and high potential difference. So that's the condition. They can ask these questions in OBJ or theory. What is required for gases to conduct electricity? Low pressure and what? High potential difference. That's the condition. So let me explain it further by saying at low pressure, at very low pressure, let me do it like this. At very low pressure and high voltage, the gas in the discharge tube breaks into ions. Positive ions move toward the cathode. Remember the law of electrostatics? Positive ions move towards the cathode because the cathode is the negative electrode. So positive ions move toward the cathode and the negative ions and free electrons move toward the anode. Keep that in mind. It's good to note that the positive ions knock off electrons from metal plate of the cathode. So as the positive ions move towards the cathode, they knock off electrons. So by attracting them from the metal plate of the cathode. So it is now good to note that the electrons produced at the cathode are called cathode rays. So electrons produced at the cathode are called cathode rays. So that's very good to note. Let's now talk about characteristics cathode rays. So number one, they consist of streams of fast moving electrons. Number two, they cause glass and other materials to glow, or we say fluorines, glow or it's just like fluorescent, glow of fluorines with greenish color. They travel in a straight line. They are deflected by electric, magnetic field. They can ionize a gas. They will turn a light paddle wheel in the tube because they have mass, momentum, and energy. They are highly energetic particles. They can affect photographic plates. They can produce X-rays from high density mirrors. When they are suddenly stopped by such mirrors. They are highly penetrating and can penetrate through metal, such as aluminum, steel, and gold foil. Now we'll go straight to the application of cathode rays. So cathode rays are used in fluorescent tube, used commercially for lighting and display signs. The tube contains mercury vapor, which at low pressure glows. Or fluoresce at the passage cathode. So fluorescent tubes contain mercury vapor which at low pressure glows when cathode passes through them. That's how it is used for lighting. Straight to, I'm going to add to this title and thermionic emission. So it's fine, even if I don't put it in the title, but we'll go to another topic. Thermionic emission. Thermionic. Just like thermionic, like combination of those two words. Thermionic emission. And let's explain that concept. Whenever a metal is heated to a sufficiently high temperature, electrons are emitted from the surface of the metal. The process known as thermionic emission. So now I want you as a student, a physicist, or whatever state you find yourself, to be able to define things after you are given what I call the backward definition, because what is just given to you right now Sometimes called that the backward definition. They just explain it by saying whenever a metal is heated to sufficiently high temperature, electrons are emitted from the surface of the metal in a process known as this. Now, if I ask you to define thermionic emission, you should say thermionic emission is the process by which electrons are emitted from the surface of metal when the metal is sufficiently heated to a high temperature. So let's write that down. Thermionic emission is the process by which a metal, by which electrons are emitted from the surface of metal when it is heated to a sufficiently high temperature. That is the idea. So let's go ahead with our discussions. When the filament is heated to a high temperature, extra energy given to its free electrons at the surface of the metal enables them to break through the surface of the metal and exist outside it as an electron cloud. So we see that. The diode valve rather. The diode valve is a simple application of the principle of thermionic emission as the diode valve. It consists of an anode, usually in the form of a cylinder. A hot filament made of tungsten. Why? And component surrounding the filament. So we need to take note of that. A diode valve is a simple application of the principle of thermodynamic convection. It consists of an anode, usually in the form of a cylinder, a hot filament made of tungsten wire, and components surrounding the filament. And it's good to note that all these components parts, all these component parts are enclosed in a highly evacuated glass bulb. Okay, good to take note of these points. Read and reread them and get the essential points from them. Let's move forward. Action of a diode. Give me a minute. Action of a diode. Diode characteristics. The filament supplies free electrons when heated by the currents from the battery. The filament supplies free electrons when heated by the current from the battery. In the anode is made positive in potential with respect to the cathode. Electrons flow towards the anode and constitute the anode current. IA, which is registered by the milliammeter. So please, if you are asked how does the diode work, this explanation is specifically for that. The filament supplies free electrons when heated by current for battery. And when we write battery as E, we are referring to EMF. That is the one that has the voltage. So let me just remove the E from there so that it doesn't necessarily cause any confusion, but just know that it is a battery. So the filament, when heated by the current on the battery, when the anode is made positive in potential with respect to the cathode, electrons flow towards the anode and constitute anode current, which is registered by milliampere. Milliammeter. Diode characteristics. A diode characteristic of shows a diode valve does not obey Ohm's law. Diode characteristics curve shows that the diode valve does not obey Ohm's law. That is why it is called non-ohmic conductor. So the diode valve is called a non-ohmic conductor. Now, what is the idea? Because the action of the diode allows current to flow only in one direction. The valve is used as a rectifier to produce DC voltage from an AC supply. So they have told you some secrets there. I just want to call this secrets because I want to use that beautiful name. Because the action of the diode allows current to flow in one direction. And that's why it is non-ohmic. Current flows in one direction. So the valve is also used as a rectifier, and the function of a rectifier is to produce DC voltage from AC supply. So please take note of these things. Let's go to the next subheading. Cathode ray oscillator. I'm not going to call it oscillator, that's oscilloscope. Cathode ray oscilloscope. The cathode ray Oscilloscope is an instrument used for investigation of current voltages in electronic circuit. It is a vacuum tube so they told you the use. They're not telling you the morphology, how it looks like. It is a vacuum tube containing an electron gun at one end and a fluorescent screen at the other end. Between these, I'm going to draw the diagram soon. Between these, are two pairs of deflector plates near the middle of the tube. So between these are two pairs of deflector plates near the middle of the tube. The electron gun consists of the heated element to supply electrons by thermionic emission. It will consist of the anode, it will consist of the cathode, also, and that's it. Okay. I would love to state that the anode acts as focusing lens to accelerate and focus electrons onto a spot in the fluorescent screen. Let me draw the diagram of this cathode ray oscilloscope rather, sorry. If I now proceed to make the last statement about it. So we have Right now, over here we have one black thing. We have one curved thing here. We have another curved cylinder here. We have one flat plate here, another opposite one down. We have one here and one here. Yeah, we have that thing passing too. Something that seems to run through all of them. All right, now this is called the cathode. Cathode. This is called the grid. It's called the anode, which is positive. And this entire tree, they make the electron gun. This pair of plates are called the Y plates. This other pair are called the X plates. And then combined, they are called deflection plates. This is the electron beam, that thing that seems to go through everything. Electron beam. And then what you have at the end here is a fluorescent screen. Fluorescent screen. Now, the idea is that, let me shift this entire diagram. This particular diagram is called the basic structure of a cathode ray oscilloscope. Okay, let me move this diagram side to up. Underline it. Let me move diagram down a bit. Okay. Let me make the last couple of statements about the cathode ray oscilloscope and proceed to the final topic. So the cathode ray oscilloscope is used for studying all types of waveform, especially the alternating current waveform. So the cathode ray oscilloscope is used to study all kinds of waveform, especially the alternating current waveform. And to measure frequencies and amplitude of voltage of electronic devices. So take note of that. Now to the final topic, which is called wave particle duality, or some call it wave particle paradox. So let's start by saying the principle of wave particle duality explains the dual nature of matter as a wave and as a particle. It explains the dual nature of matter as a wave and as a particle. Principle of wave particle duality explains the dual nature of matter as a wave and as a particle. Let's now quickly start with the subheading duality of light. Duality of light. Light is an electromagnetic wave which radiates out from its source with a velocity of 3 times 10 to the 8 meter per second. This can be used to explain the concept of reflection, refraction, and interference. What they just said now is light as a wave explains reflection, refraction, and interference. It now mentions that, I can now mention rather, that to explain emission, absorption, photoelectric effect, and radiation of energy, by heated bodies. To explain emission, absorption, photoelectric effect, and radiation of energy by heated bodies. explain emission, absorption, photoelectric effect, and radiation of energy by heated bodies, it is assumed. It is assumed that light energy travels through space in form of concentrated bundles energy called photons. So the idea of energy quantization explains emission, absorption, photoelectric effect, and radiation of energy heated bodies. So and in this case, we refer to, so this emission, photoelectric radiation, they are explained by the particle. That's photons are light particles. Are you following me? Each assumed to have energy HF. So, and this is according to Planck's theory. That's why H is the Planck's, where H is Planck's constant. So the idea here is that when we talk about wave, light as wave, we can easily explain reflection, refraction, and interference. When we talk about light as particle, photons, particles of energy, we explain emission, absorption, photoelectric effect, and radiation of energy by third bodies. Clear? Now let's talk about duality of matter. Duality of matter. Oh, we still have one more topic after this. Though these are just short topics. Duality of matter. We have one more topic after this wave particle duality. Yeah, that's something on semiconductors. So duality of matter quickly. Newton's theories and laws considered matter and electrons as particles. Newton's story and laws consider matter and electrons as particles. The Broglie postulated as an electron of mass, it's an electron of mass m moving with a velocity v radiates that an electron of mass m moving with a velocity v radiates energy and has a wavelength. So Newton, let me read that again. Newton's theories and laws considered matter and electrons as particles. De Broglie postulated that an electron of mass m moving with a velocity v radiates energy and has a wavelength given by, so commonly in the world, they call this the Broglie wavelength. And here, h is Planck's constant. We already know that. M is mass and v is that velocity. So this is commonly called the de Broglie wavelength. So, and that is this thing that de Broglie postulated, that the electron of mass this and velocity this has wavelength this. It is true. Let me put it like this: the de Broglie wavelength applies to electrons and all the elementary particles like protons and neutrons. That is the idea. There is something called uncertainty principle that we'll touch quickly before we go on. Uncertainty principle. This is by Heisenberg. Heisenberg has shown by this experiment the experiment of uncertainty principle in electron diffraction that it is impossible to know the exact position and velocity of a particle simultaneously. So if you want to state it as a principle, you said uncertainty principle states that you can state it in two ways. Uncertainty principle or Heisenberg's uncertainty principle states that it is impossible to determine or know the exact position and velocity or sometimes you say energy and time of a particle simultaneously. So you can't know position and velocity that pair, energy and time simultaneously. So this is how it is. State it like this most of the time. Change the position. Okay, let me say it like this. Instead of position and velocity, let's say position and momentum. So let's say position, momentum. So just go there. So because I'm going to write it like this, position changing x greater than or equal to h over 2 pi. And the same thing for energy and time. So whenever we write things like this, we're saying we cannot determine this and this at the same time. We cannot determine energy and time at the same time. That's what it means by simultaneously. You cannot determine or know exact position and momentum, as well as, let me put as well as here, as well as the energy and time of the particle simultaneously. So P here is momentum. So that delta in front is just changing. Then X is position. E here is energy. And T is time. So this is what the Eisenberg acceleration principle states, and this is how we write it in terms of formula. So let's dive deep straight into the final of the final topic, that is rockets and satellites. Rockets and satellites. And just in bracket, let's put basic electronics. So it is good to start by saying the word satellite. The word satellite refers to a body orbiting a larger one. So when you say orbiting a larger one, you mean moving around a larger one. So satellite is a body moving around a larger one. That's the idea. There are natural satellites. There are natural satellites. There are natural satellites, e.g. the Earth, and other planets. Orbiting the sun. There are natural satellites, e.g. the Earth and other planets orbiting the sun. And there are artificial satellites. Communication satellites. So artificial satellites are like communication satellites. For instance, that of MTN or that of your, Glow and all of that. And these ones, they transmit telecommunication signals. So we have communication satellites, we have GPS, global positioning satellite, GPS, as it's commonly called, which allows for identification of locations. That is the feature that audits our maps, Google Maps, Google Maps, then iPhone Maps, all of that. Identification of locations on the Earth. And there are also meteorological satellites. What are the functions of this one? They monitor weather and climate patterns. Take note of that. For those in Nigeria, an example of Nigeria satellite is NigerSat 1. And it is a disaster monitoring let me spell that right, monitoring microsatellite. There is another one called Nicom Sat 1, and this is for mobile phone and internet services. And this Nicom Sat 1 failed due to, or let me say, assist to function. Assist to function due to Failure of its solar cell system. So does this to function due to failure of its solar cell system. Take note of that. Let's proceed to the components of a satellite. Components of a satellite. After I talk about satellites, I'll talk about basic electronics. So let me just put, instead of a bracket here, let me put and. This is like a symbol for and. Components of satellite. All satellites have some common basic components that work together to form the following systems. Power generation and distribution system. Command and data handling system. Payload. Protective shielding. Rocket thruster system. So satellites, they have these systems. They have components as well, like they have components like solar cells. So these are the systems above. They also have components such as solar cells, batteries, command antenna, communication antenna, radio receivers and transmitters, rocket fuel, rocket motor, rocket thrusters, and cameras. That is the idea. Now let's look at basic electronics. Basic electronics. And here I'll be looking at semiconductors. Good to establish that semiconductors, crystalline or amorphous, solid, distinct electrical characteristics rather. Okay, let me put it this way. They are crystalline or amorphous solids with distinct electrical characteristics of possessing higher resistance than so of possessing higher resistance than the typical conductor. So when we say higher resistance to electricity than the typical conductor, but lower resistance than the insulators. Now, if you have lower resistance than the insulators, it means you conduct electricity better than insulators, because resistance means that is your ability not to be able to conduct. So if you have lower resistance, that means you allow electricity to pass through more than the conductors. But if you have higher resistance than typical conductor, it means your resistance, you resist electricity to an extent, but as far as it's higher than insulators, you don't accommodate electricity above. So let me tell you, for instance, if conductors can conduct electricity and they are here, and insulators which do not conduct electricity, they are here. This is where insulators, this is where semiconductors are. So the level of conductor is here, the level of semiconductor is here, the level of insulator is here, semiconductors. So yes, the semiconductor resists electricity, but it has lower resistance. And when you have lower resistance, that means you allow electricity to pass through more than insulators. But they have higher resistance than conductor. That is conductor, the conductor just allow everything, electricity. So that's why it's a conductor. It allows electricity to flow through freely. But semiconductor has some resistance that is higher than the resistance of conductors, but it is lower. So lower resistance than insulators. Then when you compare them with conductors, they have higher resistance. That is, they don't allow electricity to pass through like conductors. So that's the idea. And it is good to note that in SC, semiconductor, their resistance, take note of this point, very important, decreases with temperature. The resistance decreases with what? Temperature. This is an opposite behavior. Or you say a behavior opposite to metals. A behavior opposite to the behavior of metals. That means that for metals, the resistance increases with temperature. So, but semiconductors, resistance decreases with temperature. So it is good to note that there is a process called doping that alters. Doping is a process of adding impurities to a semiconductor in order to alter its conducting properties. So a big idea here is that doping increases the number of carrier charges. Let's do it this way. Doping increases, or let's say greatly increases the number of charge carriers. When we say charge carriers, in semiconductors, we have two charge carriers. We have holes and electrons. So doping increases holes and electrons within the crystal. So, and by that, changes the properties. So there are two major types of impurities. There are two major types of impurities. There's one called donor. And examples of that are antimony. These are names of elements: arsenic and phosphorus. And these ones, they give off electrons to produce N-type semiconductors. Give off electrons. They donate electrons. Give off or donate. Give off or donate. Or let me say donate or donate electrons to form N-type semiconductors, while the other type called acceptor. Examples of those acceptors are aluminum, boron, and gallium. So these ones now, they receive or accept the electrons to form P-type semiconductors. So The n-type contains mostly free electrons. It has excess electrons. These guys, they have excess electrons. So contain excess electrons. While charge carriers. So the charge carriers for donors are excess electrons. The charge carriers here are O's, free O's. Contains free O's. And O's are formed because there are shortage of electrons. So O's are formed because there is such shortage of what? Electrons. So contains excess O's, or we say excess of free O's. So why acceptors contain excess of free O's? We have donors contain excess electrons. So they ask what are the charge carriers in acceptors? Excess of free O's. So those are the charge carriers. So please take note of those things. A single semiconductor can have like p-type and n-type regions. A single semiconductor can have p-type and n-type regions when doped under precise conditions. The junction between the region, the P and N regions of a semiconductor is called PN junction. It is good to note some of these points before I call it a day. Doping lowers the resistance of the semiconductor. So doping is one of the ways to increase the conducting ability. So yeah, I wrote it that, doping the process of adding impurities to a semiconductor in order to alter its conducting properties. So take note of that. So doping lowers the resistance of a semiconductor. That is, it makes it tend towards becoming more of a conductor. But also permits the creation of semi-conduction junction. The behavior of charge carriers at this junction is responsible for the usefulness of semiconductors. So this semiconductor junction, this PN junction is responsible or useful for the usefulness semiconductors are used in usefulness of semiconductors. So it has uses of semiconductors in diodes, transistors, and then another one, modern electronics. It is good to note before we conclude finally that the most widely used semiconductor are silicon, germanium, and compounds like gallium, and compounds of gallium rather. So elements located where metalloids. So if you check a periodic table, elements in the metalloid section, where metalloids are on the periodic table, are usually used as semiconductors. It is good to end this particular class, and I will see you in the subsequent classes.